Oh yeah, we're going to talk about continuity in this video. What does it mean to be continuous? We're going to jump right into an informal definition of what it means to be continuous. So to have a function be continuous, what that means is we can draw that function without lifting up our pencil or pen or whatever you're using to draw. So I put my pen down and I just draw a nice continuous curve like that. And that's continuous. We'll put arrows at the end saying it goes on forever. But because I didn't lift up my pencil, it's continuous. We draw something with a point, like an absolute value, also considered continuous. Putting arrows at the end means it goes forever in both those directions, of course. So that's continuous informally. Essentially, it means the graph of whatever function we're talking about has no jumps, gaps, or holes. We're going to talk about that next, which is what does that look like? So to understand what it means to be continuous, it's actually just as important to understand what it means to not be continuous. So we're going to talk about the discontinuities, the three types. So one is a hole. Now, how does a hole occur? Well, what does that look like? We've got maybe a line with a hole in the middle of it, like that. Now, when we talked about limits earlier in the chapter, we have that the limit exists here, and that's true. But the function itself is not continuous at this x value. It's important to note that the function's continuous all along here. We have no holes, no jumps, no gaps. And all along here, we're continuous. But at that point right there where there's a hole, not continuous. Then we've got the idea of what's called a jump discontinuity. Now the jump discontinuity falls into another category called non-removable discontinuities. This hole right here falls into the category of what is called a removable discontinuity. We call it that because if I were to plug that one instant where there's a hole, this would then be a continuous function. So we consider it removable. If you think of it as data, like this is showing, I don't know, the amount of money a company has at any point in time as it goes on. Maybe it's in debt in the past and then it gains money as it goes on. And then we just don't have data for a certain day. It doesn't change the trajectory of that data. So it's considered a removable discontinuity. This non-removable discontinuity, known as a jump discontinuity, looks something like this. So I'm going to draw just a funky looking function like that. And then it's going to jump down. And that's what makes this graph not continuous at this value, this x value. Is it continuous all along this? Oh yeah. Is the graph continuous all along here? For sure. But it is not continuous at this x value. Looks like it's at x equals 0. And that's because we have a jump, boing, discontinuity. And that's actually a formal term, jump discontinuity. That is a type of non-removable discontinuity. You can't remove that. If we were to slide this graph up so that it was continuous at x equals 0, right? Fill that hole and move it up here. Yeah, that would change the entire dynamic of this graph. So non-removable. And the last type of discontinuity we will discuss is one that is known as a gap or an infinite discontinuity. And so that would be something where a vertical asymptote occurs. So something like this. Let's say we got a random vertical asymptote and I go whoop, up like that. And then even if we're agreeing with the infinity that we're going to, we're not continuous at this x value. Are we continuous all along here? For sure. Are we continuous all along here? Absolutely. But at this x value where the vertical asymptote occurs, we are not continuous. And that is non-removable for a similar reason as this is. We can't just remove the vertical asymptote and join up the curve. It changes the whole shape of the curve. So these are forms of non-removable discontinuities, and this is a removable one. Holes, jump discontinuities, gap or infinite discontinuities. Sweet. Now before we wrap up this video, I want to go over the formal definition of continuity. Now, if you don't need to know this for class, then you could stop the video at this point. But if you're in the advanced calculus AB or BC classes, or maybe your college professor or high school teacher wants you to understand the formal definition, this is for you. So let's check it out. But if you're in the advanced calculus class, you need to know this. So it says, what is the formal definition of continuity? Well, we already went over informal, which means that there can't be any holes, jumps, or gaps, what we just went over in the last page, meaning we need to be able to draw a curve without picking up our pen or pencil. So a function in words is continuous on an interval if at any point on the interval, the value of the function equals the limit and both the value and limit exist. Boy, you probably hear that and are like, what the heck does this mean? So what I figured I'd do is I would show you a situation where each of the three properties need to be satisfied and what happens if they're not satisfied, and why it makes sense that we wouldn't be continuous. So the three parts that must be true: the limit as x goes to any c value of a function f of x must exist. So let's see what happens if the limit doesn't exist. Well, a whole bunch of stuff could happen there, right? So you could have the limit not exist, and in that case, it could be something like this. So we could have a jump discontinuity, right? And so if this right here is our c value, right here, if this is x equals c and this is the curve f of x, here we've got a situation where the limit does not exist at c because the y value from the left and from the right are not equal. So we're not continuous. So you've got to have it so that the limit exists. But you also have to have it so that f of c exists. So what would be a situation where the limit exists but the function doesn't? Okay, well, I'm glad you asked. So that would be something where you have a hole, right? So let's say that we have a hole like this. Whoop. And let's say that this is the value x equals c. Well, now in this case, if we look at this function, we don't have a y value at c. However, we do have a limit as x approaches c of f of x. So unfortunately in this case, we have it so that we're not continuous at c. Are we continuous everywhere else? Sure, we are. But we're talking about at c, are we continuous? And the answer is no. The limit exists at c, but the function does not. And then last, we've also got to have that the limit as x approaches c of f of x must also equal f of c. So what would be a case where, maybe we have 1 and 2 are both true, but 3 isn't? That'd be similar to this graph. So let's say that I do another graph like it, and I have a hole. And I have f of c, but it's at a different value. So here you've got f of x is defined at x equals c. So it satisfies number 2. And you've got that the function has a limit at x equals c. However, the value of f at c is not equal to the value of f as a limit at c. In other words, we've got a hole and the value is defined, but the hole's not plugged, which makes it not continuous. So you've got to have all three conditions be true in order for the function to be continuous at an x value. And again, in short form, you're basically saying the limit and function must both exist at c, and they have to be equal. That's it. In the later on exercises, what I'll do is I will go over how to formally prove if a function is continuous at an x value. That's a challenging proof and not something most calculus students need to have down. But in the advanced calculus A, B, and BC courses, you should definitely have it down. See you in the next video. Peace.